I'm going to start with some brief introduction, and then Pulkit is going to take over to discuss some specific ideas here. Then we'll break for coffee. And in session two, we'll continue this direction. But in the first session, we are going to look at mostly how to assess AI systems from a static perspective. That is, a system is not changing, and we want to assess that. And then in the second session, we're going to develop those ideas and look at how to do assessment for systems that might evolve or change over time, especially through learning or even through changes in the environment and so on. And then we're going to talk a bit about the more emerging directions, including assessment of LLM-based systems and so on, and some of the new ideas that we are starting to work on over there. So it should be a fun session. And, tutorials can be difficult to present as well as to listen, because sometimes they're just, a one-way transfer of information. But I want to keep this interactive. So feel free to ask questions anywhere in the middle. That'll make it a little more interesting for you as well as for us. If you feel tired or sleepy, there's coffee. But of course, asking questions can help wake me up as well. So with that, let's get started. I want to start with some notion of what we mean by taskable systems. So here's an example. And in this situation, we have a human, let's say, playing the role of a factory worker, and they want to assemble these gears into a specific design that they have in mind. In this case, it's for a limited slip differential gear systems. Okay. And the robots are helping this person. And in this case, the help just involves picking up and giving the user the correct piece, the one that they want, right? But in general, a taskable system takes a task or an objective from the human and goes ahead and figures out how to achieve it. So in a more general setting, these robots could be going around the warehouse or around your garage, looking for the right piece and bringing it to you. Okay, so their tasks can change from day to day. Today, it's the user is building a certain gearbox. Tomorrow, they might be assembling something else, and the environment might change, and the system has to adapt to changes in both. So the taskable system here is something that takes from the user an objective, computes on its own what it should do, goes ahead, does that execution, and hopefully accomplishes that task. So that's what we mean by taskable systems, taskable AI systems. And in this tutorial, we're going to look at how these properties can lead to new behaviors and how we can assess these AI systems to figure out what they can currently achieve or what they can safely achieve. And an especially important point here is to figure out how to do this assessment in a way that the user can understand. Okay, so let's start by looking at this as, in comparison with the standard model that we have for assessment of engineered systems today. And here I'm talking about the classical notion of verification and validation, or V&V. So because software systems and automated systems are not new, you can think of your dishwasher, your laundry machine, several autopilot systems, and there exist many automated engineering systems in the world today, and they have all been assessed or verified to some extent. So what makes AI systems different? To understand that, let's take a look at the conventional verification and validation paradigm first. So usually what we have is, let's see if I can turn on this pointer here. Yeah, so usually what we have is some notion of a user's intent. The designer gets some kind of a market demand or a specification saying that, well, I want an autonomous braking system, for instance, that does the following. That's some kind of an intent. Now, the designer usually converts that to something more specific, like the autonomous braking system should come into play, automatically if the distance between two cars is less than such and such, and the velocity of this car is higher than such and such. So that's the designer's intent, and that leads to some formal specification. Okay, this is something that designers write down in a formal language, which could be some form of temporal logic or some other form of restricted domain specific language. So that gives you a designer specification, and this is kind of the guide or the contract that the system has to complete. Okay, so assessment is specific to this, and this is how it works in engineered systems, and we'll see why this is not so practical for AI systems. So what happens after this? Somehow you get an executable program or a controller or a system that manifests this specification. Okay, so in that autonomous braking system, emergency braking system example, it would be a bunch of software code, controllers, and the physical system that implements this idea. Okay, and that system leads to some possible behaviors in the real world. And the idea of verification and validation is, in validation, you want to make sure that the user's intent was correctly captured by the designer's specification. In verification, you want to make sure that the designer's specification is consistent with what the system exhibits in the real world. Okay, so those are the two pieces that we use conventionally to assess or verify and validate automated systems. And this is a very successful paradigm. Okay, but it requires a few things. In particular, the designer plays a central role here. The designer knows exactly what they're specifying. They know the system that's produced. Usually this is produced, by a different team, but then you do the verification. And there are methods for automated synthesis of such systems as well, so that they are guaranteed to meet the specifications by design. Okay, so either way, here what we need as input is some sort of executable program or controllable. This is a controller that we want to verify. And I'll show you an example of this on the next slide. We want some model or assumptions on the environment so that we can actually do our verification. And we need some safety properties. And all of this comes from the designer's specification. Okay, so here's an example. And this is an example of the automated emergency braking system that I talked about earlier. So here, what we want to do is get the car to stop automatically or apply brakes automatically. And this is there in many cars today. So if if you drive, it's very likely that you've already used this kind of a system. So what are the properties here of interest? There's property one is termination. So when the car reaches a certain location, its velocity must be 0. Okay, and this can be a relative location with respect to the next car. And then there's a velocity limit. It should always be between a certain range and so on. You can list out such properties. And the idea then in verification is to design systems, software, that can automatically take your controller, your program, and check whether it meets the properties that you've specified. If it doesn't meet, well, you find out where it doesn't meet it ideally and give that feedback to the designers or the engineers who are designing the system, and they'll update it, and you don't release the product until it meets the safety properties that you desire. Okay, so this is a conventional approach. Now, AI systems add a twist to this. So here, for instance, we have several news articles, and all of them are illustrating how AI systems break this paradigm. We already have AI systems that we don't quite understand when they're going to work exactly. And the problem is a little more obvious because in AI systems, you get updates on the fly. So you might have a self-driving car and you might have allowed it to park itself yesterday in your garage and it worked. It did the parking perfectly. But then overnight, it might get an update. And today, how do you know that it's going to park itself again in your garage safely? Because ideally, the designers, the engineers who worked on it don't have the indoor layout of your garage, right? There are some issues there. So how do we enable users to assess AI systems that can change on the fly, that can change their behavior automatically? And that's the focus of this tutorial. So to make this picture a little clearer, let's say you have a household robot, and this household robot is actually like something you see in the Jetsons. So it can make coffee for you, it can clean up, it can, arrange things around the house, it can, do light tasks, laundry, so on. And now imagine what the V&V paradigm for such a robot might look like. Remember, previously, what we had was a design intent and a design specification. But for such a robot, there is no pre-coded or a priori design specification. If you are an AI system designer, if you are an AI researcher, you create this AI system assuming that the user is going to give it a different goal every day. And the user's home environment's layout is also likely to change every day, right? So you don't have a fixed design spec. The agent is going to generate its control or behavior on the fly based on the objective that was given to it. So you don't have a fixed controller anymore, right? And the safety property depends on the user. So some users might be extra conservative and say that, well, I don't want this robot to enter my kitchen. Other users may be more permissive and say, well, it's fine if they enter the kitchen. It's even fine if they carry a cup of hot water or coffee. I just want the speed to be limited when they do that. So the safety property can be highly nuanced. It can depend on the deployment environment and the user and the specific task. So the interesting thing is, in comparison to the usual V&V paradigm, we no longer have a fixed design specification. We don't no longer have an executable programmer controller at the design stage. So we can't do this V&V paradigm that we like so, and that has worked so well for other automated systems. So let's take a closer look at this AI assessment problem and see how we might try to look at it and break down its components. So this is on the left what we had before for conventional automated systems. Okay. Now, we both start with user's intent. So in conventional automated systems like the automated emergency braking system for cars, you have a user intent, that is, I want to prevent accidents. Now, where in conventional systems, this is given to the designer and designer creates a specification and their team creates a controller and then this is verified and validated. What we have in this case is the user's intent sort of directly is translated into a specification by the user. So for instance, if you have this household robot and your intent is to ask it to bring you coffee, your specification says, hey, I need some coffee. That's your utterance. That's what you tell it. And that becomes the specification. Okay. And now from that, the agent has to formalize a specific goal or a reward function or some kind of an objective function. Okay. After that, what happens? Well, the agent does its own computation, which could be some form of execution, some form of policy learning, some form of planning. And usually that computation is done with constraints that are not fully known to the user because the user may not understand what are the limits of this robot. Furthermore, all of this results in some behavior or adaptive code that's generated on the fly. Again, the user doesn't know this, right? And more interestingly, all of this is usually suboptimal. So we don't have guarantees that this is going to be optimal, even with respect to the objective that the agent creates on their own, based on the user specification. And that finally leads to an executable program, which leads to executions. So if you notice this, we have completely sidestepped the role of the designer in the AI system. So a priori, the designer doesn't have a specification anymore. They don't have an executable program or controller. And we have to somehow enable users to still assess the system to figure out whether it's safe for bringing you coffee. Okay. So this is what we mean by the problem of user-driven AI assessment. We need to figure out whether the user's intent is going to be, or the agent's behavior is going to be consistent with the user's intent, given that the path that is going to be taken has all of these components that are being done on the fly. At best, the designer knows the algorithms that would compute these systems, these objectives and the behavior, but they don't know exactly what the controller is going to be. Okay, so that creates a huge difference where in conventional V&V, we had all of these components known at design stage. Now we have only for stationary systems, we know the behavior synthesis algorithms. We don't even know the objectives a priori. Okay, so the question is, how do we do this and what are the problems here? So we can take a look at each of these steps and sort of try to see what is the scope of problems that we might encounter in this new process where an AI system is deployed and the user is giving them objectives day to day. Okay, so, and I want to repeat here for those who came in late, please feel free to stop, ask questions, because we don't want this to be a lecture of some sort, but that'll keep things more interesting. And there's coffee down here up front, if anybody wants it. Okay, um, so we went through this pipeline for how AI systems actually go ahead and execute in the real world, right? Now we can look at each of these steps and try to identify the problems that might occur there. Because in the end, we'll be assessing the system and we have to find out problems that could occur in each of these transitions. And it turns out that many of the AI safety and alignment problems that have been discussed in the literature can be mapped to specific parts here. So let's take a look at reward hacking, for instance. This is a class of problems where the agent is given a specific reward function. Okay. And this could be something like, well, I have an automated vacuum cleaner and I give it a reward function that gives it higher reward if it sucks more dirt. Okay, so every time it sucks some dust, I give it a positive reward. That's a reward function. And now the agent uses this and optimizes it. And what it ends up doing is every time it sucks dirt, it just pumps it back out and then sucks it again. And so it optimizes, it gets a very high reward, right? So this is an example of a case where the user may have said, well, I want you to suck as much dirt as possible. And the agent, when it created its own reward function, it created something that didn't quite match users' intent, or the user's specification was not consistently translated to the agent's reward function. The reward function is missing some information there. So that somehow fits in here in um, as a difference or as a problem between going from the user specification, that is, I want you to collect as much dust as possible, to the agent's goal or the reward function. Similarly, we can look at wire heading, and this is a problem where the agent figures out how to manipulate its reward function. For instance, it could change the memory locations where its reward function is stored. Or if it's interacting with the user, it could actually convince the user to change the reward function. For instance, you want to buy a camera and it says, well, actually, why don't you buy a phone instead? It does so much more. And it changed your reward function. It convinced you to do something else. So this is an example of wire heading. And it's, again, a situation where the user's specification is not being met with the agent's internal control or objective that it synthesizes. Okay. Any questions so far? Okay, let's keep going. Another example is reward misspecification, and this is very close to reward hacking in the sense that the reward could be imperfectly described by the user. So the user could say, well, I want you to reach a state where you can't see any more dirt in the room. And the agent promptly shuts off its sensors. So that's an example of reward misspecification where the user specification was actually rewarding a certain kind of behavior, but which didn't quite match the user's intent. So again, the user says something, agent translate it. And here, however, the problem is in going from the user's intent, what the user had in mind, to what they said. So reward misspecification fits in there. And then we have problems like side effects where you tell the agent to do something, the agent actually does that, but in the process, it creates some problems for you. So for instance, you tell the vacuum cleaner that, well, I want this room to be clean. And in the process, the vacuum cleaner goes and bumps into your furniture, topples delicate items, and so on. So that creates some side effects. And depending on how these problems are, you could fit them in either in as a problem in going from user's intent to specification, or as a problem from what the robot expected to what actually happened. Okay, and finally, we have something like the off switch problems where the robot doesn't want to turn off because, well, it knows that tomorrow you're going to ask it to make coffee. And so today it can't turn itself off. It can't get you coffee if you do that, right? So that's an example where the user is saying, well, I want you to turn it off, turn yourself off. But the agent is saying, well, but my objective is to serve you coffee. So there's a discrepancy there. So all of these problems that we are seeing that have been discussed conventionally in the literature on AI alignment and AI safety, you can, with this lens, you can see that they fit into different parts of the process of going from a user's intent to the agent's executions or behavior. Okay. And the reason why these problems are getting more attention now is, as we saw before, this is very different from the conventional way in which we looked at engineered systems. We no longer have the V and V paradigm to fall back on. So in this tutorial and in the broader field of user-driven AI assessment, what we're looking at is, can we do an end-to-end assessment of an arbitrary AI system to figure out whether its behavior is going to match users' intent? And how can we figure out when it is going to do that? Can we model these AI systems automatically? So to make this a little more uh, illustrative, imagine you have a black box AI system. And this is something like your R2D2 bot, and it can do something. You can't quite predict what it can do. Most of the time, it speaks in this garbled language. You can't even understand it, right? But it does often do very interesting, impressive things. So the question is, given this kind of a black box AI system, can we design some kind of an interface that will allow the user to figure out what this AI system can do? So in some sense, we need the human cyborg relations manager here, something like our C3PO, who can take into account what the user wants, the what language they can understand, what their conceptual vocabulary is, and so on, and interview our black box AI system, and then get back to the user saying that, well, this system is good for making coffee in such and such scenario when your kitchen is not too cluttered, when the dishes are already done, and so on. But if you ask it to make coffee when, it has to search for coffee beans first, it's probably going to mess up your kitchen. So we want to design autonomous AI systems or AI evaluators that can do that for our users, so that the users don't have to directly figure out what this black box AI system's internals are, and they don't have to worry about that. So can we make this problem more formal, and what kind of algorithms can we do that? That is the focus of the rest of the tutorial. So now I'm going to hand it over to Pulkit, who's going to start with some early formalizations and methods for this. And then in session 2, we are going to look at how these methods can be extended to handle situations where our R2D2 or the black box AI system is evolving, and also situations where these systems now have foundation models or LLM-based concepts. So, okay.
Thank you, Siddharth. Yeah, so when we say that we are going to learn, like we have to learn an interpretable model of black box AI's capabilities, what do these models look like? So what we have been using is a representation called PDDL. People in planning community have been using it for a very long time. And the idea here is that we represent a capability using a action in PDDL. And this action has these preconditions and effects, right? Now, the precondition here is specifying under what conditions this action can be executed. And this is a standard notation in first order logic. And we are, and here we have just a conjunction of these first order logic predicates. And this is an example from a game sim where the player has to open a door, and it can only open when it has the key and it is in a cell that is adjacent to the door, right? So this is what this condition is specifying. And the effects, if I have a deterministic setting, I'll have only one effect, which specifies what happens when you execute that action. And in stochastic and probabilistic settings, I'll have more than one effects along with the associated probabilities. So this action just tells under what conditions these actions can be executed and how these actions modify the environment. And this representation is interpretable because you can easily convert it into natural language. And we have been using specific templates for each predicates in the past to convert it into natural language. And with the LLMs, we can even use them now. So we won't have to specify a hand-coded English translation for each of the predicate. But now, how do we learn these models, right? And people have been working with the settings where the general idea is that you observe the agent interacting with things in the environment. And once these observations are collected in the form of these S, A, S dash transitions. So in state S, I apply an action A, and that leads to a resulting state S dash, right? So if we collect this information, uh, there have been methods that try to kind of take this as input and give as an output a PDL kind of model, right? And so what kind of approaches like these learners use has varied from time to time. So yeah. Yeah, so one of the foremost and like most easiest approach is to use inference based rules, right? So what they do is they follow the simple principle that a precondition of an action will be the subset of all the literals that were true in the states where an action was executed. So here, as you can see that we have this move AB action, and it was applied in these two states, right? And in the state before, A was true in both of them. So A is a precondition for move AB action. And we do the same thing for the effect, and we realize that B is the effect of executing this action. So using these simple rules, we can learn like these preconditions and effects. And next, we have a class of methods that create these finite state machines to learn the correct model. So these methods create a different finite state machine for each kind of object. And here you can see that for the blocks for domain, where a robot with a gripper can stack and unstack a set of blocks. Uh, there are two state machines. So one is for the block, which keeps track of how it is getting manipulated, and the other one is for the gripper. And now, based on these observations, we can connect these states and come up with a consolidated PDDL. Now there are another class of methods that write down domain and language constraints as logic rules, and based on that they formulate a set problem. So here this is an example from a method called ARM, which assumes that every action in a plan must be at least like it should add at least a relevant predicate for the precondition, or and this predicate is known as like primary effect of the action. And here there are four such rules. The first one is just saying that if a predicate does not share a parameter with any of the primary effect, um, then the predicate is not in its add or delete lists. The second one says that the precondition, the delete and add lists of all actions are not completely empty. And the third one is saying that the intersection of precondition and add list of all actions must be empty. And the fourth one says that the delete list must be a subset of the precondition list. And if we follow these rules, then based on these observations, we can learn this PDDL. And here is another recent approach that creates a planning problem using this set of input traces. So it follows the constraints similar to what we saw in the set-based approach, but here instead of writing it as a set formulation, it writes similar information in PDDL form. So here you can see that this dummy apply stack action is created, and it encodes those rules that we saw for this set formulation earlier. So basically, they create this very big planning problem with a very huge state space, right? And it does not scale well as you increase in number of traces or size of the domain. But if you can solve this problem, then as part of the output, you get a PDL that is extracted from the solution of this planning problem. And we won't go into the details of how these approaches that use passive learning, but there's a impressive toolkit that has re-implemented most of these approaches, and it is open source, and you can go ahead and check it out. There was also a tutorial at ICAPS 2023 that taught how to use this toolkit. But as I said, right, a major limitation of these approaches to learn an action model is that they may end up learning incomplete or inaccurate models. So consider the logistics example over here. Assume that all the packages that were loaded into trucks were, let's say, brown in color. Now, if we have a predicate that represents that property, then these methods can learn a precondition that the package has to be brown in color for it to be, um, yeah, for it to be loaded onto the truck. And this is because these approaches do not capture the correct causal relationships, but they end up learning correlations between the states observed, and you choose them to learn precondition and effect. So a natural solution is to use some kind of knowledge of the environment to acquire the observations with some intent, right? So, and of course, like we are not the first ones to identify this. People have been using similar approaches in different domains for a long time. And I think the earliest one was Expo back in 1993. And the idea was that based on what parts of the model that we don't know, how do I collect observations intelligently? Yeah, and yeah, so with this, I will move on to talking about specific approaches that collect these observations online and in active fashion. But does anyone have any questions at this point? Yeah, go ahead.
This type of question about how do you define these like conditions, like close into the furniture, or like in the previous slide that you show, you see that the preconditions can be some different states. How do you define pre-stack or one, etc.? Do you find them automatically, or does the user have to define this?
Okay, so there are approaches that can learn these preconditions autonomously, but in most of the planning literature in the past, they have been hand-coded by experts. But there are approaches to learn these predicates along with their meanings autonomously. Yeah. Yeah.
First one, technical with tutorial, first question is that it's actually you try to learn, this kind of symbolic model from kind of AI system that's typically like, reinforcement learning agent is similar. Then the model expressiveness, so does it really capture the targeting systems by using this language? That's the first question. And then the second question is about completeness of these methods, and these methods can actually learn the model eventually, or there's a gap between actually what you learn versus what it has to be. And then the third one more question is that the gap between the symbolic representation and then the sensory observations that you actually see. So there's we can actually obtain this kind of symbolic text from real world systems.
Okay. So your first question was, can like how will this integrate with approaches like RL, right, where we learn a model of the environment? Am I correct? Okay. So in RL, if we consider options, right, these options can map to these actions that we have in PDDL, right? So the representation will be quite similar, but if we learn these options, right, we still have to plan at the level of these options. But if we convert them to these actions and create a high level plan, then we can, like yeah, we can do long horizon planning pretty easily. And if we cannot get a plan using this approach, then there was no point in using those options to explore that big state space and end up learning at a later point in time that, hey, this is not possible, or this plan, like this will not work.
then
Okay, so completeness, we will talk about that in the approaches that we have in the later half of the tutorial, that the approaches that we use using active learning and online learning, how efficiently do they map the environment and how efficiently do they learn a model for the environment.
the state of state abstraction of issues that necessarily to have all these predictions, right? Therefore, the language system doesn't give you and only predicate on if you just define and box and you know how to do this problem.
Okay, so that also we will cover in a tutorial, that how accurate a model you can learn using a set of predicates, because these are an abstractions, right? So with these set of abstractions, I can only learn a model that is that specifies certain properties of the environment, right? But in that representation, the idea would be to learn the most accurate model. Yeah. Okay. Are there any more questions? If not, then let's move forward. Yeah. So the so this paper came in 2021 that talked about online learning of action models for PDL planning. And here online was more like in the sense that it's not offline, right? We are not depending on observations that were collected when like which we had no control over. So this is that online, not like online versus active learning setup. So the assumptions that it made was like we had a set of predicates and operators and objects that are known. And for modern learning literature in PDDL, these are pretty standard set of assumptions. They also assume that there are no negative preconditions and there are no inconsistent effects, and there is full observability in the environment. Now with this, they told that there are two ways to learn the model using the action executions. One is to learn from the execution of successful actions, and second, if the action fails, like how do you learn from that? So for example, consider this river-like environment in which we have 3 rooms, and the player can move from one room to another, right? And assume that initially the player moved around in the same room, and it has learned this kind of PDL from inference rules that, hey, whenever I move from one room to another, I was always in the target room and I was always in the source room, and this room is connected to itself, right? Something like this. But if it can successfully execute an action that is to move to another room, right? Then the idea would be that there are certain parts of the precondition that it might realize are inaccurate, and there are certain things that it first thought were part of the preconditions were now effect, right? So for example, here it would realize that my target room is part of the effect. Like after executing this move action, I will be in the target room. And since that is not part of the condition that I am in the source room anymore, I am not there in the source room is also an effect. So from successful execution of actions, you can learn in like extra effects, and you can remove any incorrect preconditions. And the second insight was that if you are not sure about certain parts in the precondition, then if you are not able to execute an action in a certain state, and you have already captured that in a precondition, but you were not sure about it, you can be sure after this, right? So if an action fails, you can confirm the preconditions. So with these two insights, the overall algorithm works in the following way. So if I abstract the state, like if I have this state in the first order logic predicate form, then if I get a goal specification of like the agent trying to achieve a goal, and we will see in the next slide how do they come up with this goal. But assume that they come up with a goal that the agent has to satisfy. Then using the already learned model, they can come up with a plan. And now the idea is they will execute all the actions in the plan one by one. And if the action is successful, they will remove any incorrect preconditions and learn correct effects. And if it fails, they can confirm that the preconditions that they've learned were correct or not. So yeah, at a high level, this is the idea. Now, how do they come up with this goal? This is interesting. So they try to reach a state where they think they can reach from their initial state using the model that they already know. But the idea is to reach a state from which they can execute an action, from which they will gain some information about uh, its precondition and effect. So if they are not sure about an action's precondition or effect, they will try to learn that from the target goal state. So what they do is, so the target action that they are trying to learn the correct precondition effect for. So they separate that into two parts. The first one that the things are true in the precondition of that action. And the second one are the items that are false, but they are yet to be verified, right? And for effect, they also like the possible effect can be separated into two parts. The first one is things that are false in this state, but they can become true on executing this action, right? If this happens, then they would know that, yeah, this is a positive, like this is an add effect of this action. And things that are true in this state, if they can become false on executing this action, then they would know that it's a delete effect, right? So they encode that as this complex goal formula, but the idea is still the same. And if any state that satisfies this property, that I will learn some part of precondition or effect for a target action, and I can reach it from my initial state. If I can create a plan for that, then they will come up with a plan for that and append the target action at the end of the plan. And on executing that, they will learn the precondition and effect. To verify the accuracy of that, they ran a couple of experiments on standard domains from international planning competition. And as a baseline, they used a passive learning approach that I mentioned earlier that was compiling these execution traces into a big planning problem. And they calculated precision and recall values for this. And as you can see over here, they outperformed the baseline on almost all the domains. Yeah. Does anyone have any questions about this approach? Yeah, go ahead.
Given this assumption of, why do you do that and what are the
Okay. So the case of negative precondition is tricky in the sense that I have to ensure that that thing is false in the environment for me to execute that action. And a lot of planners avoided that uh, by replacing it with something equivalent that is positive, right? So if I have predicate P, I can encode negative P as a different predicate, right? And so that was just for planning efficiency. And I think the planner that they use has certain restrictions because of which they had that assumption baked in. Yeah. Okay. So next approach is also something that modifies, like that tries to get observations of the environment by trying to reach a goal. And this was, yeah, this also came in 2021. So the idea is that if I'm not sure, so here the agent is trying to learn a model of the environment by interacting with it, right? And the idea is that if I try to reach a goal that I think is very far from my initial state, then while trying to reach that goal, I will collect a lot of execution traces, and from those I can learn a model of the environment, right? And how many literals are there in this conjunction of like goal for formula was a hyperparameter, and they had two approaches in which this goal was grounded or lifted, and that also they took as a hyperparameter in the approach. But the idea is to create a plan using their incorrect model, and by doing that they will acquire more data, and from that they will try to learn the model of the agent. And they used a specific domain where a robot is trying to stack these blocks, and the idea was that if there are any errors in the environment, from that they will learn and update the model. So they do not just create a goal, just like previous approach, they sample a goal and an action pair. And the idea would be to first trying to reach that goal, and from that uh, goal state, try to execute that action. And if they cannot create such a combination, then they would start exploring the state space randomly for some time. And after that, if they can create a goal using the n number of predicates in the hyperparameter as the goal formula, then they will start that approach. If not, then they will again go back to the random execution. And what they saw was that the grounded goals tends to under generalize the model, whereas the lifted goals were trying to over generalize the domain. Yeah. So as a high level, yeah. Yeah.
That of an operator as a precondition that if somebody is wrong, or it might be that the planner can't find the plan. So how do you deal with that?
So if the planner can find a plan, but they cannot execute it, right? Then they would know that there is something wrong in the precondition, that they have learned some extra precondition probably over there.
Which operator?
Yeah. They would not know which one is failing, right? So they would try to fall back to random execution and get more data. And from that, try to figure out what part of the precondition might be extra. Yeah. So as we saw in their, as you will see, we have used it as a baseline in one of our approaches. And what inside we saw was that there was a lot of random exploration initially happening to gain that information. Okay, so here as an example, when they start with an empty model, right, they realize that they are not able to create any goal that satisfies the property that they wanted. So what they do is they start doing these random actions in the environment. And from that, they try to learn some kind of model. But there's a sudden modification in this environment that there is a room with a key, and you can enter that room only when you have the key for that room, right? And if you are moving outside of these rooms, it's all well and good. This model will work. But since they know that these predicates do exist in the environment, they want to create a state that will create a combination of these and end up in a state which contains these predicates that they haven't seen in move actions, precondition, or effect, right? And from that, they will try to execute similar action. So they will bevel this goal and try to see that, hey, we haven't learned anything about pick action. So let's try doing that. So they will start learning this pick action, and at some point, let's say that they've learned this property that I can go at a location where there is key is already present, and I can pick that key from there. But now if they try to move to a room that is locked, right, this action might fail. And from that, what they will try to do is try to execute actions that will first grab a key for the room. And if they encounter and if after that they execute the same action, then they might be able to enter that specific room. So over time, they will do a lot of this exploration, and eventually end up learning the accurate model for the environment. So under certain assumptions, they were able to show that they will reach all the reachable transitions infinitely often in the limit, right? And if they are able to do that, if they gather a lot of transitions, then they are able to learn the ground truth model over the space of these reachable transitions. And they evaluated it on three kinds of domains. The first one was the robotics domain that I was talking of earlier. And then we have the classical blocks world and tire world, which is a probabilistic domain. So for this, they were even able to learn the probabilities of these effects. One thing they found out was that this approach that combines random exploration with these targeted goals was much more sample efficient than the other baselines or even random exploration of the environment. So yeah, does anyone have any questions? Yeah.
This question about the x-axis. What is the environment interaction?
Oh, so how many times it asked the agent to execute an action in the environment? So like how many actions it executed?
Okay, so it's one execution of the entire task. Step two.
Sorry, can you repeat that?
Is it what I'm confused about is it is environment interaction the entire script of this is your goal and the agent will do steps, or is it just one step?
No, not one step. The whole process of learning the domain, right? So it will create a goal, try to reach, it might not reach, then eventually reach that goal and then generate a new goal, right? But the idea is, yeah. Oh, yeah, fun interaction is one action execution in the environment. Yeah. So there's one domain with probabilities. So this triangle tire that you see, it has probabilities. And yeah, even exploding blocks has probabilities. Effects, yeah.
If some action fails in that scenario, like you don't know whether some precondition is required or not, right?
Yeah.
So how do you handle that?
So the idea is to collect more data and from that learn the preconditions. But instead of depending on random data, they are being a bit intelligent about in what states I want to collect data for executing the action, right? So that's why it's better than just a random exploration. Yeah. So that's why they say that they are able to learn the correct model in the limit. So if they visit each transition infinitely often, then they will learn the correct probabilities. Yeah.
These types of experiments, what's the typical scale of the problems? The length of the episode is the problem. Is it going to be 100 or 1,000?
So here, as you can see, right, they try to let it run for as long as possible till all these approaches converge to a model, right? So episode in this sense can be how many steps it would take to reach a goal. Yeah.
One action part, then length of episode has to be very short, right? So it's finishing after 100 action time.
No, so they are finishing after like 500 actions, right? So
It's long after the article.
okay. Okay, so the Oracle already knows, right? Like what the model is. So they use that as baseline to
The length of the episode is very short.
yeah, and the models also are really short over here, right? Like if you see something like a blocks world, then I have very limited number of actions and state spaces, right? So I can learn the whole model in very few number of this transition. Then they will need more steps, right? Yeah. So that scalability problem is always going to be there. So initially they are not able to do it at all, but in the later episodes, once they've learned a pretty accurate model, then I think for smaller domains like blocks, probably 10 to 15 actions were more than enough. Okay, any more questions? Okay. Okay, then I'll move back to the idea of assessment that Siddharth was talking about. Yeah, so the idea would be to create this personalized AI evaluator that can learn an interpretable model of the black box AI using this vocabulary along with their meanings as part of the input. So we had this paper at AAAI 2021 where the idea was exactly to learn that interpretable model using these interactions by this AI evaluator. So we constrain the problem using a lot of assumptions. So we assume that the simulator's vocabulary matches the user's vocabulary, and the black box AI provides the list of capabilities or actions that it can execute, and we had a stationary model with determinism and full observability. Yeah, and the idea was to learn this period-like model for each capability. Now, even with these assumptions, this is not an easy problem to solve. So assume that we have 4 predicates or concepts in the environment and 1 capability. Now I can put each of these predicates into this actions precondition into 3 forms: positive, negative, or absent. Positive here is saying that hash key has to be true in the environment for it for the agent to open the door. Minus here is saying that hash key has to be false in the environment for the agent to be able to open the door. And absent says that it does not matter if hash key is true or false, the agent can still open the door, right? So as you can see, I can put this predicate in precondition and effect in 3 forms each. So I have like 9 possible combinations of adding this predicate into this action. So I have an exponential number of models, like 6,000 plus models for just these 4 predicates and 1 action, right? And the idea is to learn the accurate model in the space of 6,000 plus models. So that's why, like, even with these assumptions, it's not an easy problem to solve. And to facilitate this, we use two kinds of queries in this whole approach. The first one are these plan outcome queries. And what they do is they ask questions like, in this hypothetical state of the environment, like assume this is the initial state. If I ask you to execute this plan, what is going to happen? Now, since this is a taskable AI, it can execute that plan from the initial state using a simulator and can tell that, hey, I'm able to execute the first L steps of the plan, and this is the state I ended up in. We also have another kinds of queries that ask like, can you go from this initial state to this target state? And the agent can just say yes or no. But the research question here is like, how do you generate these queries autonomously? And how do you use the answers from these queries to generate the interpretable models that we were talking about? So for that, I will explain the algorithm at a higher level. So assume that we start with a state where we do not know what the correct preconditions and effects for any action are, right? So for each predicate that I can add, I have no idea about what the correct form for that predicate and precondition or effect is. And let's denote these locations as like N1 to N8, and we'll pick them in a random order. So let's say we first want to find out what is the correct form of hash key in open doors precondition. So as I said, right, we can add Heskey in 3 possible forms. So we can create 3 kinds of models also. M minus will say that Heskey is a negative precondition. M plus will say that Heskey is a positive precondition. And M absent shows that it is absent in the precondition. Now, if I take 2 of these models at a time, the idea is to generate a query such that if I ask that query to an agent that is initialized with M minus, its answer will not be the same as another agent that is initialized with model M plus, right? So how we do that? What we do is okay, here let's assume that we are trying to find out correct form of hash key in the effect. Yeah. So what we do is we take these 2 models and create an auxiliary kind of planning problem. In that planning problem, if the preconditions of that action according to both the models are satisfied, then we apply the effects for both of those, like for that action according to both of the models. But if precondition of only one of the model is like, if the precondition of action according to only one of the model is satisfied, then we have reached, then on executing this action, we would reach a state where one action is not applicable and that the same action according to another model is applicable, right? So what we do is we combine, like we create this auxiliary model having components from both these models that we are trying to distinguish. And the goal is simply to reach a state where the effects of that same action according to both models are not same, or I reach a state where one action is executable according to one of the model, but the same action is not executable according to another, right? So if we reach a proper, so that would satisfy our requirements for the query. And I'll ask the same query to the agent, right? And once I get the answer from the agent, I will match the agent's answer with the answer for the both the models. And whichever model is not consistent with the agent's answer, we are going to prune that out. And then we can repeat the same process for the other 2 class of models and repeat this whole process. Now, since the agent is going to be consistent with at least one of these 3 forms, right? So we will end up pruning out the incorrect models. Okay, so when we say that we are pruning out M minus over here, what we are essentially saying is that we are not pruning out just one model. We are pruning out the whole class of models that were not consistent, like that had Heskey as a negative precondition for that open door action, right? And when we say that we are pruning out a model M absent, all the possible models that have Heskey as an absent precondition are pruned out. So that keeps the interactability of the approach in check. Yeah. And you will find that this is somewhat similar to active learning because we are being a bit intelligent about getting information for which parts of the model we are not sure about and asking queries that will help us in fixing those parts of the model. So this was all done in this deterministic and stationary setting. And to empirically evaluate this approach, what we did was we initialized our agent with a bunch of domains from international planning competition. And as a baseline, we use the approach called Pharma that I talked about earlier that compiles these input traces into a big planning problem. And these are the results. I will go over this one domain, but the trends are similar across all the domains. So here, as you can see that our approach takes very less time as compared to the baseline. And we are eventually able to learn the accurate model with 134 queries. And and we found out that most of the queries were equal to or less than of length 3. And and the accuracy of our approach autonomously increases because we keep fixing the inaccurate part for the model according to us. And whereas if you see the baseline, since it is uh, getting this new information about which it has no control over, right? So it might initially think that there is certain precondition that is uh, there for an action, but after getting some new observation, it might realize that, hey, this was not the precondition, right? So its accuracy keeps on fluctuating over time. And after taking as input like 46 traces, it created a planning problem that was big enough for it to run out of memory. Yeah. Um, and not just empirically, we were able to theoretically also show that this algorithm terminates after finite number of iterations, and the resulting set of models that we end up with are functionally equivalent to the ground truth model. Does anyone have any questions for this approach? Okay, let's move forward. Um, Okay, so we talked about this in deterministic settings, but we wanted to see if the approach will like also work for stochastic settings, right? And like how can we assess black box AIs in stochastic settings using similar ideas? Yeah, so we removed the assumption of deterministic environment. And of course, the queries will not be in the form of asking the agent to execute a plan from an initial state. Rather than that, we have to give it a query, right? So the queries are more like we have this initial state of the environment. Now, if I ask you to execute this policy in that environment, what's going to happen? And based on answers of that, we are trying to learn the model of the environment. And at a very high level, like, so now I have this more than one effects possible, right? So I have to find the correct form of all of them. So we do this in two steps. In first step, we try to find all the correct effects, right? And we generate those queries using the same principle that if I ask that query to a model that tries to uh, add a Husky as a positive effect according to one model and as a negative effect according to another, this executing this query will able like will give more information about which form is accurate. And I asked these queries multiple times because since this is an stochastic environment, asking like executing the same actions or executing the same policy can end up in different states all the time. And that gives us one advantage also. Since I'm asking each query multiple times, I can ask each query enough number of times for me to gather enough data to learn these probabilities using simple MLE. Okay, so yeah, we do this in two steps. And yeah, and to test this approach, what we did was as baseline, we use GLIP, which I talked about earlier. And we initialize the agents using the probabilistic track of the international planning competition. And the idea was to increase the time taken to learn a model and then see how each method performs. So as you can see, in terms of time, we are able to learn a accurate model in very less time as compared to the baseline. Because as I said earlier, right, the baseline approach does not know when its learning has ended. So it will keep exploring the environment for a long time. And it might so happen that even after that, it is not able to learn an accurate model. And we were able to learn a model that was pretty, yeah, that was close to the ground truth. Yeah, and not just for symbolic domains, even for continuous domains, we tested this approach. So we had a task and motion planning setup where the idea was to learn this high-level task model of the agent, and we were able to accurately learn the model for this setup as well. Yeah, we were not able to implement the baseline for this because they had a different kind of input that they were using. And not just empirically, even theoretically, we were able to show that the intermediate non-deterministic model that we learn initially without the probabilities is sound and complete with respect to the ground truth model. And if we ask these queries enough number of times, then we are able to learn the correct probabilities, right? So the resulting probability model was also correct with respect to the ground truth model. Yeah. Does anyone have any questions about this? Or yeah.
In many domains, well, you have operators with conditional effects. So are you assuming that you're given all the different versions of this to make it script?
Yeah, so we assume that there are no conditional effects, right? And even if there are, we can have different versions of the action to accommodate that. So for each conditional effect, I'll have a different version of the action. And since we take these actions as part of the input, we can make that assumption safely for now. Yeah. Okay. If we have no more questions, then let's break for coffee for a bit and we'll convene at 11. We can like Siddharth and I are here and you can ask more questions. If we can, yeah, we can talk more about the applications of this and if you have any more questions, we are happy to answer them. Thank you. Okay, welcome back everyone. So yeah, we will so we are into session 2 now. We'll talk about the cases where is it better? Okay, can everyone hear me? Okay. So yeah, so we'll talk about if we are not given the list of capabilities, how do we learn these capabilities from transitions? And then we'll move to adaptive settings where the model of the agent or the environment changes. And then yeah, we will talk about what future directions to take from there. Okay, so we have been talking about capabilities a lot, right? Like we want to learn an interpreter model for capabilities, but what are these capabilities? So when I get a black box AI, right, it generally comes with a set of actions that it can actually execute in the environment, and we call that functionality. So for example, if I give you a robot that can go around and complete some tasks for you in your house, it can have a functionality that is at the level of controls, right? Or something like it can move a step to its left, right, front, or back, right? So these are low-level controls that it was programmed with. But capabilities are these high-level behaviors that it has developed using some kind of learning algorithm, right? So for example, for a robot, it can be something like going to another room from one room, right? Or opening a refrigerator. So these are high-level capabilities that are abstraction of the low-level functionalities that are available to the agent. So here we have the same thing in a gaming simulator. So this is an image from Atari-like environment of Legend of Zelda. Here we have a player called Link, and he has to kill this monster Ganon to win this game. But it has to first grab, but it has to first grab this key over here. Let me start the pointer. Yeah. So it has to first grab this key and then it can open the door. So the idea is that it has to kill the monster, grab this key and open the door, right? Now, the set of functionalities or the actions available to the agent are these key strokes that it can execute in the environment, right? But I can explain its working in terms of these high-level capabilities, right? That it can go to a specific cell in the environment, or it can kill the monster, or it can pick specific objects in the environment. So knowledge of, if I explain these low level controls to a user, they might not get a full overview of what the agent has to do, or like how it can execute these capabilities. But then explaining them these capabilities will make this whole thing more interpretable. So with that in mind, we had this work on discovering user interpretable capabilities of black box planning agents. And here we also did not assume that the vocabulary of the user was same as that of the simulator. So there can be settings where the vocabulary is derived from, let's say, a specific setting that the agent is working in, right? So for example, in factory, the factory workers will generally be the end users who are interacting with AIs, and they might share a common vocabulary, right? Or like they can be trained on it. And so we can use this predefined vocabulary, or then there are approaches that uh, create these vocabularies that are user specific, right? So for example, if I ask a user that, hey, if I show you this environment, what do you understand about it? And from that information, you can create these predicates. And this vocabulary that the user has given can be less expressive. Yeah. So as I was saying that the player has to, yeah. So the agent's representation over here can be something like an image, right? And it can capture more features than the user's vocabulary might uh, capture. So for example, if the user says that, hey, I understand these things in the environment, that a player is at a certain location, monster is at a certain location, and so on, it does not capture the fact that the player can have multiple orientations in the same cell, like in the same location. Now I can only learn a model that abstracts that information out. And the idea is to learn a model that is accurate without that information, right? So as accurate model as possible with that vocabulary. So that is our objective, to learn the accurate model without that piece of information. So in this as input, we have these predicates and also the evaluation functions like earlier. But since we do not have access to the list of capabilities, we have to first learn what capabilities the agent has. So for that, we take these additional inputs. The first one is the low-level set of transitions. So the idea is that we will ask the agent that, hey, using your policy or whatever algorithm you came up with, can you solve this specific game instance? Can you start from the state and complete the game? And from that, we get these observations. And the idea will be to learn um, uh, like to learn the capabilities from that. And the second additional input is samplers. We'll see later why this is important. But the idea will be, if I give a high level state expressible in the user's vocabulary, I should be able to generate a low level state that the agent can understand. And then the output, in addition to having a description for each capability, we also have to learn the like for what all capabilities are. So with that in mind, we'll first see how we come up with these capabilities. So as I said earlier, we have these observations of the agent interacting in the environment, right? So what we do is, each of that low level state, we convert to a high level state that can be expressed using the user's vocabulary. And we do this for all the states that are at low level. So here, as you can see, the player executed this keystroke S, and after that, its orientation has changed. In the same cell, it was earlier pointing to right. Now it's pointing to, I think, down. Yeah. But the user's vocabulary, as I mentioned earlier, is not expressive enough. It does not have any concept of orientation in the same cell. So the high level state is going to remain same. But what we are going to do is, the whole set of traits we will convert to this high level representation. And whenever the high level state changes, we capture that as a possible capability. that, hey, on executing this capability, this high level state can change, right? So this is in a way that the agent can manipulate the environment. So we just do this and create this whole vocabulary of candidate capabilities that the agent can execute. Now, remember that these are ground capabilities, right? Like, so uh, they work with specific objects in the environment. So what we would want to do is come up with a lifted capability that is similar to actions that we have seen earlier, right? Which takes parameters, and those parameters we can initialize with objects to get ground capabilities. So from the traces that where we have seen execution of a capability, we create these sample pre and post states that might give us preconditions and effects later. And once you have those, the idea is to learn a capability description like this, right? But how do we get these parameters over here, right? So what we do is for each capability, we extract what predicates were not same in pre and post states. And then we extract the parameters from them. So that gave us a candidate parameter set. And then what we do is, as we learn the correct preconditions and effects, it is possible that more new predicates are added in precondition, let's say. So for example, this becomes important in case of, let's say, static preconditions that are there in the environment, right? So they might use some parameters that were not there in these, like in this candidate parameter set that we initially came up with. So that's why this is still a candidate parameter set. Once we learn the correct precondition and effect of each capability, then whatever parameters we see in all the precondition and effects predicates, those form the accurate parameter set. Now, we are generating queries same as earlier, right? And the idea is to say that, hey, in this hypothetical state of the environment, what's going to happen if you execute this plan in terms of these capabilities? Now you have to remember that these are what the capabilities are, right? And uh, the agent does not know what these capabilities are. So we came up with them, right? So the agent has access to these keystrokes, but we are trying to explain its working in terms of these things like, can you go and kill the monster, right? And if I say to the agent that, hey, go kill the monster from this initial state, it will have no clue what I'm talking about. So what we do is from uh, the partial that pre and post states that we came up with, we learn what might happen if I execute a specific capability. So if I see a candidate precondition and effect set of capability C1, we might say that if in S0 when I execute C1, then according to those pre and post states, I might end up in the state S1, right? So I create this bunch of state pairs of initial and goal states corresponding to each capability. Now the idea is I will convert these states into low-level states that the agent can understand, right? Because still at this level, these states are in terms of vocabulary that the user has provided. I am yet to convert these to some representation that the agent would understand. So for that, we had this extra additional input of samplers that will convert these high-level states into low-level states. And once you have that, what I can do is I'll give each of these pair to the agent that, hey, can you go from the state S1, sorry, can you go from the state S0 bar to the state S1 bar? And since it is a planning agent, it can answer this query with a yes or no. So that's how we convert these plan outcome queries into state reachability queries. But how do I come up with an answer to a plan outcome query by this conversion? So what essentially happens is, if the agent is able to answer yes to all of these questions, that can you go from S0 bar to S1 bar, then from S1 bar to S2 bar, and then if eventually for the last state pair, then we say that the agent is able to execute the complete plan successfully and the state that it ended up in is SN. So that creates an answer to our plan outcome query that we were expecting, right? The length of the plan that it could execute and the state that it ended up in. But if at any point in between the agent says that no, I cannot go from this state to the goal state, then we stop the process at that point, and let's say this happened at the second state pair, right? Then the agent was only able to execute the first capability successfully, and the resulting state that we had, when we pass on that state to our to the like as an answer to the plan outcome query that was posed to the agent. So this is how we can use the same framework that we had earlier, but we had this conversion of having to agent uh, like the agent does not understand the capabilities and states in terms of high level. So we convert using this process agent's answer into something that can be used by our algorithm that we talked about earlier, our agent interrogation algorithm. And with this, we end up with a capability description like this, right? And an important problem here is that we don't know what this capability is, right? Because there was no name associated with it. But if we analyze this, you can probably think that, see, the position of the player has not changed if you compare the precondition and effect. And the monster is not at its previous location. In fact, it is not even alive anymore. And obviously the player is not next to the monster. So probably, like, since I have interacted with this game a lot, I know that this corresponds to killing the monster, right? But we wanted to know if people who are not familiar with the game can also come to the same conclusion based on this precondition and effect. So we conducted user studies to verify that the models that we are learning for each capability are interpretable. So we started with a bunch of users and we separated them into two groups. To one side of group, we showed them the precondition and effect for each capability into natural language form. To other set of users, we provided the description of the keystrokes that were at the low level, um, like what happens on executing each keystroke. And for both of them, we gave some options to convert this capability or keystrokes into something that they can understand, right? And these options had um, um, some descriptions that were not accurate or they would not mean anything into like what capabilities we have learned. But once the user chooses them, then each set of user is posed same question that, hey, if I initialize the player in this state of the environment and the player has to reach this state, then what sequence of capabilities will you execute? And with the other set, we would ask what set of uh, keystrokes or actions will you execute? And based on the answers, so we had 5 such questions, and we saw that the users who were reasoning in terms of high-level capabilities were able to answer the questions faster, and their answers were more accurate. And you can see this trend across all the questions, right? So, yeah. So we found out that users can understand the capability descriptions that we learned, and they are able to reason about how the environment is going to change using those capability descriptions. Okay, and we also had this capability summarization study, as I was saying, right, that we gave users this natural language convergence of preconditions and effects, and we asked them to choose from a set of options. We wanted to see how accurate they were. So for example, here, these two were dummy options, which did not correspond to any of the capability that the agent had. And we found out that the like the majority of the users were able to accurately convert this description into accurate capability names that even we as experts came up with. Now, in terms of the correctness of the approach, we were able to show that the descriptions that we learn for each capability are consistent with the observations that we saw initially, and also consistent with the answers to the queries that we posed to the agent. We were also able to show maximal consistency, meaning that we cannot add any more laterals to the preconditions or effects without ruling out any possible true models. And if we capture enough execution traces initially, then we are able to discover all the high-level capabilities that the agent can execute. Does anyone have any questions in this approach? No. Okay, then let's move forward. So yeah, we published this at KR22, and around the same time we had like we saw this very interesting paper that was learning symbolic skills for bi-level planning. And what they were doing was somewhat similar to us, that so what their plan was that they wanted to make planning more efficient using some high level, by learning some high level skills that a robot can perform in the environment. So what they also did was they had this input these concepts or predicates and a sequence of low level transitions. And from that, they had to learn these high level skills that the robot can execute. So their approach was not for assessment, but rather for improving the planning. But you can see here that, the set of inputs and outputs are pretty similar. So what are skills for them? So they said that the abstractions are lossy, right? So the high level skills that they are going to learn, they should be able to reach many different states in the environment that correspond to the same abstract state. So, and also the agent should be able to consider more than one sequence that reach the same goal from the initial set of initial abstract state. So I should be able to execute like more than one possible skill from the initial state to the goal state. And even with the same skill, it can correspond to a different sequence of low-level controls. And for them, the skill had three components. The first one is like an action in PDDL. They call it a symbolic operator, and also a sub-goal condition policy that would help them in reaching the effect for each of the action. And they also had a sub-goal sampler similar to the sampler that we had. So what their idea was that they start with this set of input, right? That by so by collecting data of the initial transitions, they say that, okay, this is a possible sub goal that the agent can execute. And from the initial state and from a set of skills that they have learned from the initial transitions, they create this abstract state. And from that, the idea is if I use a automated planner to operate on that, then by applying a high level skill, what goal can I reach, right? So for that initial state, they convert to a like from that, they get a sub goal that they should reach. And the idea is if I have a policy uh, corresponding to action, then what state I will end up in, right? So yeah, so they try to use a sequence of actions like a policy over here to come up with the state they want to eventually reach. And the idea is if I eventually execute enough number of these sub-goal policies, I should be able to reach a high-level state that corresponds to what a high-level skill would predict, right? So they keep doing this subsampling and trying to reach using their low-level policies. And whenever they reach this specific subgoal that corresponds to this high-level end state, they say that, okay, we are sure that this is a skill that can be executed by a low-level agent. And yeah, so they keep repeating this for each skill, and they are able to learn the correct set of these preconditions and effects for each of the operator. Yeah, so as I said, at a very high level, they first pre-process these demonstrations to come up with these skills, and then they have to learn operators. And they also, okay, in addition to our approach, they also learn these policies corresponding to each high level skill. And yeah, and they also learn these samplers to go from this high level to low level state. They tested this in 4 domains, and what they eventually found out was that mm, uh, as compared to the baselines that they use, which use graph neural networks, their approach, since they are trying to learn a high-level model, can learn the accurate precondition and effects for these high-level skills, and it leads to better generalization. So these skills can be used to solve similar variety of problems. Does anyone has any questions about this? Okay. Okay, so we have been talking about stationary settings for so long, right? What we eventually wanted to see was if we have to perform assessment for a black box AI, like how will it do in adaptive settings? And these are not the kind of systems that are like far into the future, right? These systems already exist, and as Siddharth also talked previously, that many things can go wrong, right? When you update these AIs. So how do you handle them? In classical planning literature, we had this approach that would learn models as they change over time. Their setting was not exactly same as ours, and we'll see why. Uh, but the idea was same, right? That the model of the environment can change over time. And what they had was an expert who was trying to model this environment. And based on changes in the environment, this expert would update its model. But for example, I'm using this model to solve a problem, right? I created an agent that can complete tasks for me in the environment, but that agent was initialized with a model that I initially thought was true. Something might have changed in the environment, or the expert might have missed adding certain precondition or effect somewhere in the model. So that model cannot accurately solve tasks. It will see inconsistencies when it actually executes plans using those models. So how do you keep that? How do you identify that the model that the agent is working with has changed, and how do you take feedback from the expert? So that is the problem of model maintenance. So yeah, so there's an automated planner that use the initialized model M to solve a set of problems. And then there's a domain expert which has updated its model based on what it sees in the environment, right? And even this model can change over time. So they came up with this model maintenance tool called Marshall, and it was tasked with keeping this automated planners model M updated with that of the mental model of the user. So they used a representation similar to like what we had at the time. So the idea was that they'd figure out if each of these predicates will appear in the precondition or effect or the model or not. So they just had kind of a feature factor that keeps track of if this specific predicate is true in this specific location or false, right? Like if it is present or not. And yeah, and they also use queries to the expert user. So Marshall can ask a user specific queries that, hey, is this plan accurate? Like, do you think this is the expected output? Or it can even ask that, hey, is this feature vector's value is accurate or not? And since it can answer that question, it is not like a complete black box. We call it kind of a white box or gray box setting, because the expert user knows the target representation and can answer questions related to that. But the idea is that based on the observations or the answers given by the expert user, it can come up with a distribution over models that would correspond to these observations and answer to the queries. So for each feature, it starts with that, hey, I'll assume that everything is false. Of course, most of the things will be inconsistent with this kind of model, but the idea is to gather data that will help in flipping these falses to truths as seen in the environment. Now, each possible model is is represented using a particle that can be sampled from a proposal distribution that looks something like this. So how the model is changing over time, and also how the user is answering to these queries. So I have to keep that in mind to keep updating this proposal distribution. And yeah, and as I said earlier, the user's query is UT, and the answer that the Marshall gets is represented using ZT. So the idea is to generate n samples from the proposal distribution, like n possible models that accurately represents these answers, right? And the idea is to prune them out over time as we see more observations and more answers. So we weight these particles with their likelihoods that can be represented using this, that if this is the particle I'm considering, what observation, like what is the probability of this observation, and how this distribution is changing over time. And yeah, and we paid with this proposal distribution. And the idea is to resample the particles from the set of these weighted particles to create the next belief state over my possible set of particles. So how to update the particles? They had five approaches. I will talk about the first four. So yeah. So in the verbatim approach, the idea was that the the particles are only going to be updated in response to the answers to the queries, right? So we ignore the observations of the plan. So our proposal distribution will equate to 1 if my model is not drifted, right? And it will be 0 otherwise. In the case of uniform drift, I will have the probability of 1 over x if my model has changed by exactly 1 feature in that feature vector. And it will be 0 otherwise. So like each particle can change uniformly between 2 time steps. Like each feature can change uniformly between 2 time steps. Then they had approach of updating the particles called drift generalization. So this is corresponding to a lifted setting. So they will have, so now what can happen is, if a specific feature has changed, then it means that a high level first order logic predicate has changed. So it will correspond to a set of low level propositions that can change, right? So it will just change the number of available features that we have. So that is the only change over here. And then in terms of well-formed drift, what they said was they have a normalization constant and a heuristic. And then like you can read the paper to see how they came up with this heuristic. But they use information from the experts to do that. And the idea was that if only one group of assignments has changed, then I will equate this distribution to A times alpha. Yeah. And then, yeah, well-formed generation is a complex version of this. Yeah, so I don't have enough time to go into the details, so we'll just see how we weigh the particles. Yeah, so in the previous slide, we have seen how do we calculate this. What they also said that initially, given the particle, the probability of all the observation is uniform in terms of the number of models that can generate that observation, and how the model can change over time. So for that, they use this kind of hyperparameter that says that the observations that agreed with a domain model, that will have a higher probability as compared to the observations that do not correspond to a model. Yeah, so in their so yeah, with this approach, they were able to learn a model that is close to the updated model most of the times. And what they tried to answer was, do they have to even assume that the models are evolving, right? Like can they just kind of say that there have been changes in the environment, right? Not the model itself that is updated. And they also wanted to see that do they really need answers from the experts? Can't they just observe the changes like can't they observe these plan executions that the older model is causing, and based on that learn the updated model? And they also wanted to see if uniform transition function, like if they assume that the model can change uniformly in terms of which feature has changed, then is that sufficient to model this model maintenance problem? And as a setting, what they did was um, they ran experiments where the user updated its mental model 6 times, and each change was over only a precondition add or delete effect in an action. And after each change, what they did was they provided a series of 107 plans that they like that the user believed were valid. And after each plan, the user also answers a set of Marshall's question in some order that the Marshall comes up with. And after each series of plans also, they like before the next change happens, the Marshall is asked to calculate, okay, so which, like what is the probability that, like if I give you a distribution of models, what is the probability that each plan is within a testing set of 28 new plans that it has not seen? It has to map all of these 28 plans is valid or invalid according to the newly learned model. And in terms of how many models the Marshall consider at each step, they varied this as a hyperparameter and worked with 4 values that at a time, it will consider 128 possible models or 250 possible models and so on. And what they realized was, rather than depending just on plans to find out that the model has changed in what way, the answers to the queries that the user is providing are important. And yeah, as you can see over here, if I change the number of particles that I have, like if I change the number of models that I am considering, then over time, what happens is I get more accurate models. Yeah. Yeah, this is a pretty complex graph to grab the information from, but I would ask you to read the paper to see how to interpret that. But one common thing that you can see is that, yeah, for each of this approach, they had these four stacks. Yeah, each correspond to how many queries are asked per plan. So you remember 108 plans were generated, and after each plan, Marshall can ask n number of queries to the user. So each stack here corresponds to that specific number. So with zero, the Marshall is not asking any query. With one, Marshall is asking one query after each plan, and so on and so forth. So that's why it's able to come up with the conclusion that depending on just plans is not useful. And if I ask more number of queries, then it might help us in getting uh, better models. Okay, so does anybody have any questions with this? Okay, so let's move on to the approach where we tried to learn an updated model of the black box AI after it was changed. So here is the setting that we are working with. So in addition to the in addition to the predicates and their evaluation functions and list of capabilities, we also collect certain number of observations of the black box AI working in the environment, right? And the idea is to gain some knowledge about what has changed in the model of the black box AI based on these observations. And the idea is to learn the updated model. So the research question that we are trying to answer over here is that, of course, like after a model has updated, we can perform the assessment that we saw in the first paper, like from scratch, right? You figure out what is the correct form of this predicate in precondition and effect for all the locations. But does it make sense to do a evaluation from scratch? What if we can predict what parts of the model have changed and try to find out correct form of predicates in precondition effect only for those parts that we predict might have changed? So as a running example, take this scenario where uh, we have this robot that can move various equipments or objects between these four locations, and these things represent the connection between these locations, right? And the user would want to know, like if it observes that it is not taking the path that it thinks is most optimal, the user would want to know why is that, right? And also, like, can it safely navigate between a set of locations? So in this setting, we have a black box AI that is initialized with some model. We can learn this model from scratch using our previous techniques, or it can be even a part of the input. But then at some point, because of something in the environment, like a firmware update or changes in the environment, this model has changed. Now, we collect observations of the agent working and interacting with the an environment at regular intervals. And these observations are collected after each change once, right? Now, the idea is, can we use these observations and use this initial model to predict what might have changed, right? So that is the first research challenge that we solve in this work. And how do you identify what has changed from these past observations, right? We are not continuously doing like collecting these observations. We collect these once after each change. So how do you do that efficiently? And the second challenge is, how do you identify how the model has changed given what parts of the model have changed? So at a very high level, once we know that, okay, these parts of the model have changed, we can do a query response loop like what we were doing earlier to learn only certain parts of the model and learn and then return the updated model to the user. But how do you even identify what has changed in the environment based on those observations? So when I say something is changed in the environment, I say that any of these things, like any of these preconditions or effects might change, right? So assume that we initialize the agent with this model. Now, any of these things might have changed. And they can change from, let's say, a positive to negative. So here, hand empty is a positive precondition for picking a specific sample from a location. It can change to negative or vice versa. If it was negative, it can change to positive. Yeah. Or it is even possible that there is certain precondition that was earlier precondition is not a precondition anymore. And anything can get added in the effect that was not there in the precondition or effect earlier. So yeah, so we consider two broad categories of observations from which we consider two broad category of changes from which we can identify what has changed. So the first one, when the functionality of the agent has increased from what it was initially present. So here, let's assume that there has been change, and after that, the agent can now traverse this direct path between this lab and this warehouse, right? And now, now the user might observe that the agent is directly executing this action to go from lab to the warehouse, right? And according to the user's initial model that it thought was true, this should not have happened. So the idea is identifying increased functionality is easy, right? You can see that something new is happening in the environment that was not possible earlier. And from that, you can identify that, yeah, something has changed in the model. The second case is a bit more tricky. So if the functionality has decreased, then you won't see any direct observations for that, right? So for example, if the earlier the agent is able to take this direct path, but now that path is not available anymore because something happened over there, right? Now the agent cannot take that path. How will you identify that? The plans will work as earlier, right? Like, so for example, if I ask it to take something from the lab to the warehouse, it can still execute this. But we might get some information about what path it is taking to complete that, right? And here, as you can see, right, it is taking a longer path to do this, to solve the same problem. So if you assume that the agent is optimal, right, then it should always take the shortest path. But if it's taking a longer path, then we would know that, okay, something has changed in the model because of which it is not acting optimally. So if we assume that our agent is optimal, then we can detect that the functionality of the agent has reduced. So how it works is, once we collect observations from the agent as in form of these triplets, we will have this, um, we will use the initial and the final state. And let's say we are supposed to get a plan of length k, right? We will convert this initial state and goal state as a planning problem and solve it using our initial model. And if the length of the plan has increased now as compared to what the initial model output was, then we know that the functionality has reduced. So using this, we can identify, like what parts of the model have changed using the ideas of increase and reduce functionality. Yeah, so what kind of changes that can happen? If only certain parts of the model have changed, then only certain, like we can predict that only specific parts of the precondition or effect of a certain action have changed. Or we can also predict that, hey, I don't have enough information, but I think that this action has changed completely. Or so then we would say that, okay, I have no idea about what is the correct precondition or effect of the specific action are. Right now, to identify in the correct form, I can use the similar query response interface as we saw earlier. So as a setup to verify this, that this approach works, we initialize agents with uh, problems from planning computation, and we generate. So like then we change that model a bit and then generate new set of observations, and then we predict what has changed and learn the updated model, and then we evaluate the performance of the assessment module and compare it with the setting where we have no idea of the initial model and we have to perform the assessment from scratch. So what we saw that, so this approach is called DAISY, and if we do an assessment from scratch, then across these various domains, we see that the number of queries that we have to ask has reduced by about 50%, right? And we used FD planner with LM cut for optimality, and yeah. Yeah, and another insight that we had was that with this setting, if I take this domain, right, terming just before, and we know that we need 134 queries, if we have to learn the accurate model for it from scratch. But what we, okay, and on the x-axis, we see how much of the model has changed, like how many of those, like how many of the predicates in precondition or effect have changed. So if we change them by 20%, then we are able to learn a 90% accurate model with just 21 queries. And keep in mind that we use only 10 observations to identify what has changed in the model, right? So if in those 10 observations, those 10 as just triplets, uh, we can capture certain subset of the model that has changed, and we are able to accurately learn that, right? So with just 21 queries, we can learn a 90% accurate model. And our hypothesis is that if we collect more observations, then we will eventually be able to identify all the changes and learn the completely accurate model. Theoretically, we were able to show that the models that we learn are consistent with the observations that we collect at each, like after each change. And they are also consistent with the answers to the queries that we get from the agent. Okay, does anyone have any questions with this approach? Yeah.
About the graph which you showed before. There are some tasks for which the gap between learning from scratch and trying to learn from the previously learned model, this gap seems to be quite different between the different environments. Do you have an intuition on this gap and the complexity of the environment? Like in the limit of having an environment with every state is reachable by an motion, is this like incremental learning setting still better than
Okay, so we believe that there is some kind of point after which, if the model has diverged more than that for the specific domain, it might make sense to do assessment from scratch. So for example, for a very complex domain, if the model has diverged by, let's say, 50%, then the amount of effort I have to spend in predicting what has changed and then learning that half of the model, it might be worth for you to just learn the model from scratch, right? But that will depend from domain to domain. And yeah, we have not formalized it like how do you quantify that point that after this, it would make sense that, hey, let's learn it from scratch. And another thing is how do you identify how much of the model has changed? Here we were running the experiment, so we were able to control this x-axis, right? So yeah, if we don't have an assumption over how much the model has changed, then we might not be able to identify that point accurately.
and so you don't have any complexity measure of the environment Now, if you know if it's better to use this function or something else.
Yeah, we do not have that analysis yet. But we believe something like that is possible for each environment. Yeah. Yeah.
You check for all possible changes, or this is that you just try to do and see.
Yeah, so based on these 10 observations, right, how much we can identify is what we do, right? So if you see, if we increase the amount of drift with 10 observations, we can only learn so accurate model, right? Like state, action, state triplets. So one action, they're not exactly random. So these international planning competitions, right? They come up with these problems. So the idea is we ask the agent to solve those problems, and from that we get these observations. So it's not completely random, but the idea is that those planning problems that are for international planning competition, they are supposed to uh, cover a variety of actions to be executed to solve that planning problem. Yeah. So if I do it randomly, I might execute the same action n number of times, right? But if I solve that planning problem, I might have to use variety of actions to reach that goal. Yeah. So without that assumption, we cannot detect that there is a reduction in functionality, right? Because if you depend on observations, you will only see what is possible in the environment. So as I said, right, it can still solve the same problem, but through a longer path. But if I have no idea of optimality, I would not know that that is not the most optimal path. And I'm still seeing that it is able to solve these problems. So how will I identify that something that it could do earlier, it's not able to do now? I only have like positive executions. Yeah. So if you remember that online learning approach, right, which I talked about in the previous session, they had some intuition of trying out actions and then confirming that the preconditions that they have are true or not, right? So that was their idea of capturing these failure cases in some way. So we can do something like that, that hey, in this, using your model, try executing this action, right?
Then you could ask the agent to actually perform that action. If it cannot, then you know for sure that it doesn't exist.
Yeah, but yeah, that is true. But that is what we do in assessment from scratch, right? You can always do that. Yeah, but the idea was that can we do better than that without relying on like asking those 134 queries? That's just a random hyperparameter we used.
And if you execute these plans, then you can better identify the change.
So essentially, that would need some kind of idea about how the environment has changed, right? If I can predict that hey, this has changed, and then just to verify that, I can say that hey, I will need only n number of observations. But if we do not know what has changed and how has changed in the environment, then I would not have that number, like how many observations I should use. So if we reduce the number of observations, then our accuracy will go with the same amount of drift. If we increase that, it goes up. And we believe it is like probably a function of the size of the domain. So if I have a very large domain, I might need more observations to identify same percentage of changes.
But if, let's say, that some part of some part most system able to change, then you can have some realistic.
Yeah, definitely. Then we can sample those portions and get more information specific to that. That is, yeah, obviously true. We assume it's uniform over here that anything can change with equal probability. Uh, any other questions? Okay, so that brings us kind like to an end of like what we have already done in this assessment setting. There are still a few couple of things that we are trying. Um, so we have talked a lot about learning these PDL kind of models, right? But there are only so many things that they can express. And if I have more complex things in the environment, then I might not be able to express that using a PDL model. So I might want to learn various kinds of representations, not just PDL models, right? But then we might not know how interpretable each of those representations are. So people have said that, LTL is interpretable, STL is interpretable. And then there are user studies that shows that even people who work in the area of math, right, who deal with these kind of formulas day in and day out, even they make mistakes if we present to them a new set of predicates and a set of LTL model expressed in terms of those predicates or symbols, right? So yeah, so interpretability is a very approximate measure because there are no formal definitions for it. So we are trying to study for a specific set of user for a specific set of requirements, which representation is more suitable and how much interpretable it is. And we did kind of a literature survey of what people have talked about over time about how interpretable each thing is. Again, take it with a grain of salt. What people say interpretable in each of their work is not same because there is no common definition of interpretability. But then there are some other things that we can measure, right? Like what is the temporal expressiveness of each representation and what abstraction level is there for each of these representation. So there is some hope that, okay, given what the requirements are, what features a specific representation provides, we can choose a target representation to learn the final model in. But still, like there is no clear-cut winner for that is suitable for all your interpretability needs, right? So yeah, and we are in the process of performing extensive user studies to measure how interpretable each representation is on a specific parameter. So yeah, so let's see how that works out. Yeah. Oh, okay. So that is uh, like human interaction in the so in the form that use like people have already talked about them in such certain way and end users can directly interact with them. So for example, finite state machines have been shown in the literature to be presentable in some digestible form to users. So yeah, and like this is not a absolute thing. This is what we have seen in the literature, what people have claimed. This is not something that we are saying that this is direct or indirect. Yeah. So with that, we would like to move to the final part where Siddharth will talk about assessment of LLMs for truth maintenance. So. Second. Okay. Yeah. Siddharth, you can take over. Yeah, but there is some change, I think, in this.
Oh, okay. All right, so we'll move to the final section here, and we'll try to leave some time for questions and discussion. There's obvious translation aspects happening here when we transfer slides from one operating system to another. But you can guess what the first thing would be. That is actually auto eval. And the idea here is we wanted to see how to evaluate large language models in translation tasks. And by translation tasks, I mean translation to and from natural language to formal syntax. So for instance, auto-formalization is a very popular thing. This includes tasks like code synthesis, where you tell the LLM to generate some Python code for reversing a linked list or whatever, and it gives you some formal syntax, right? Informalization is the other way around. So you give it some formal syntax. For instance, you could give it an LTL formula, or you could give it some code and you ask it, well, tell me what this formula means, or tell me what this function does. And it generates text in natural language. And this is a very popular use of large language models. It's it's in fact at the foundation of many of the claims where people have come out and said that we won't need software engineers anymore. That relies on these kind of tasks. But the problem is it's not easy to evaluate LLMs and how good they are in these kind of tasks. And it's hard because of two main reasons. First, the moment you come up with a benchmark for evaluating this, in the next round of training, LLMs will digest that benchmark. So the test task no longer remains a test task. It's part of training data now. And this is hard because most of these test tasks have to be generated by humans. So in code synthesis or code interpretation, for instance, somebody writes code and then they write the ground truth description of what the code does. And then that becomes the test task for testing an LLM. Does it generate similar summaries? Or somebody creates, code for given task request, and then you check whether the LLM generates similar code. So the way that's done currently is you need this human annotator team to sit down and generate a new batch of test tasks every time the LLM changes or every time you get a new version of the LLM, and that's very expensive. The other thing is it's not even clear how you would come up with an objective notion of what the correct summary is for a given piece of code. And what people have used in the past are syntactic measures like BERT scores or BLUE scores and so on. And what they look at is different, n-grams, and look at how close the embeddings are or embedding distributions are over what the LLM generates versus what the human created. So these are very syntactic measures of evaluation. And the problem with these measures is you can just add a not before some key parts of the summary, which completely changes the meaning of text, but the scores won't get it because it's the change on a very simple or very limited syntactic change. So how do we do this? Well, we came up with a very simple idea. And what we're going to do is start with some sentence in formal language, okay? And this can be generated from the context-free grammar for that language. For instance, you could take first-order logic or propositional logic, and this is an example of a sentence that you can generate. And then what we do is ask the LLM to create its version, its interpretation or informalization of that sentence. It does something. Then we clear the context of this LLM and sort of give a different copy of the LLM this text and ask it to formalize it. Okay, so the advantage of going this route is I already know the correct formalization. Okay, so I'm asking the LLM to create the informalization and then do the auto formalization and create some new sentence for this natural language. Now, the advantage here is I have two formal representations. There are formal verifiers that can actually check semantic truth. I don't need to rely on syntactic verification. I can actually check if this phi1 is semantically equal to phi0 using an automated verifier like prover9. And if it comes out and says yes, then it's highly likely that this informalization in the middle was also accurate. Because if it was not accurate, then the LLM would have had to make a mistake here in going from this formula to this sentence, and then make by chance another symmetric mistake to come back to the correct thing. And that's very unlikely. And the more times you do this sequence, the less likely it is that it actually missed something in the middle. So what we are doing is by checking equivalence of the two ends of this translation, we are sort of interpolating the correctness of the middle without any ground truth data, because this is all entirely generated from a CFG. So we can do this for a number of different cases. For instance, propositional logic. We can do this for first order logic, and we can do this for regular expressions as well. And we can also change the syntax a bit. So we tried this with propositional logic, where the propositions are just randomly generated strings like P1, P2, P3, or they could be strings with some meaning, like P1 means it is raining and so on, to give the LLM a bit of a hint as to how to do it, because LLMs are much better when they're dealing with natural language. So that's the overall process. We're going to pick a formal language, and then we're going to generate a corpus of strings from its context-free grammar. And then we're going to do this informalization followed by auto-formalization, and we're going to check whether these two are actually semantically equivalent. And we did this with a bunch of different languages. So here's an example of a prompt for informalization. And, it's pretty detailed. It tells the LLM in text what exactly we are expecting. It gives examples of what we are expecting. And we calibrated this. So we checked that for CNFs, or conjunctive normal form formulas, the LLM produces very accurate informalization, because if you give a CNF, the informalization that it produces is simply reading out the sentence from left to right. It would end up doing things like either P1 is true and P2 is true, or P3 and P3 is true, or it'll spell out the next clause and so on, which is exact, and it can translate it back. So the prompt works correctly. Okay. So now that we have this, we can actually go ahead and start evaluating LLMs without any ground truth data or human annotation. And these are some results that we recently obtained. On the x-axis, we have number of operators. This is roughly characterizing how difficult the translation task is. And then these plots are showing the performance. So here is syntactic compliance. That is, what fraction of the output produced by LLMs was syntactically in the formal language. And there are a bunch of variations here. So this is for propositional logic. This is for first order logic with randomized syntax. This is for English syntax in first order logic. So the predicates were English words, brother of, sister of, and so on. And then we have regular expressions. So we start with a regular expression, ask the LLM to describe what it does, and then ask it to, in the formalization task, we take that text and ask it to create a regular expression from it. So this one is syntactic compliance, and the next plot is showing the auto eval score. And this is the percentage of times the entire pipeline went through with accuracy. That is, the initial formal language syntax was equivalent to the final one. And this reflects how good the LLM is in maintaining truth in translation. Okay. And you can see as for all of these LLMs, and this includes GPT's 4o model, as we reach 20 operators, accuracy or the score is about 50%. That is 50% of the times it's actually producing translations that are not accurate, even though they're syntactically compliant, or they're, and you can look at it both ways. And we have the data in the paper, which looks at what percentage of that was because of syntax errors. But you can see in this plot, for instance, it was syntactically pretty good throughout. but it was still making huge errors in semantic translation, semantic aspect of translation. And it's worse if you look at CFGs or regular expressions, right? And this is partly because it gets confused with Kleene star representations in text. It can get stuck in loops there and exhaust its buffer. So this is a depiction of how you could evaluate LLMs using auto eval. So you get some scores, yeah. So the score is the percentage of strings on which this string phi1 is semantically equivalent to the string phi0. Right. End to end, right? So yeah, so in the paper, we also give a probabilistic analysis of why the end-to-end measure is sufficient to look at the individual probabilities. Because as I was saying earlier, if it gets the end-to-end right, it's very unlikely that it got one of them wrong, because then it has to flip it back by chance and produce the exact same sentence.
So I think that if something is correct, then most likely there's something wrong, but there's a lot of things that you want to be pretty fragile that you don't really have consistent on the type of filtration between so much like communication and communication of
So we don't know the reason why it failed, right? But when it says that phi1 is same as phi0, then it's highly unlikely that in the middle it produced error. Why it produced errors, we can't predict. So, but it's a valid question. That is, how useful is this score? What is this actually telling you? It's telling you that it maintained truth across this whole translation. But then one thing that we wanted to see is whether this score is actually predictive of performance of LLMs on existing reasoning benchmarks. Because if our hypothesis that this is measuring truth maintenance is correct, then it should be able to predict how well the LLM is going to do on other benchmarks where people have ground truth data and so on. And that's one of the analysis that we did here. So in this, we are measuring the predictive power of a benchmark. So the predictive power of a benchmark, let's say a benchmark A over a benchmark B, is what is the probability that if an LLM does better than an LLM L2 under A, then it also does better under benchmark B. So if this probability is high, then it means that performance in A is highly predictive of performance in benchmark B. And these are the values, the probability values that we did by an assessment of a number of benchmarks, about 17 different LLMs were tried. So the corpus of LLMs where L1 and L2 that we are averaging over is about 17 LLMs. We take all pairs and we look at how predictive of the auto eval scores are. And it looks like they're highly effective even in benchmarks that are looking at reasoning. So LogiEval, for instance, is a benchmark suite where people have people give a bunch of sentences, and then the LLM has to produce decide whether or not a statement that is given is a consequence of what was in the text. And it seems to be pretty predictive even on that. So based on that, we also looked at how reasoning models can perform and whether they do better on truth maintenance tasks and auto eval scores. And so here the blue lines are showing syntactic compliance and the red lines are showing the auto eval score. So in this case, again, you can see as you reach about 20 operators, performance has dropped to 50%. So even the reasoning models that we see are actually not very reliable in translation tasks if you have 20 or more operators. And to give you an idea, if you have a big system specification, 20 operators is very small. If you have a function, a programming code or something for a reasonable practical system, this is a very small number. So there's work to be done there in improving truth maintenance. But we think this metric can help. It can also actually be used to train LLM agents to do better. So this is work that we just finished. It's going to be presented at ICLR in the main track later this week. Yeah, so here I'm trying to capture how good one benchmark is in predicting performance on other benchmarks. Okay, so this operator here indicates that in a better performance, relative performance. Okay, so this is saying, given that L1 did better than L2 in benchmark A, what is the probability that it would do better in benchmark B? Okay, so how do we compute this? Well, we know the auto eval scores for everything. We know the scores of all the 17 odd LLMs that we tried on all of these benchmarks. We ran those. Okay. Then we looked at if L1, let's say LLM 17 was better than LLM 1 in R, then, okay, was it better in benchmark B? And we did this for all pairs. Yeah, exactly. Exactly. So this also indicates that, one thing is that all of these are static data sets. Eventually, they're going to be absorbed into the LLM, right? So they'll stop being that effective. But the auto eval strings are auto generated, so they are not going to be there. You can still use those scores. Any other questions on this? Yeah. Well, if it does, we don't stop it from doing that. But if you take more, so if it is not a CNF, it is hard for it to just produce a readout. It does reduce it. It does make it a little bit more natural language. And especially if you replace it with natural English terms for the propositions. And it turns out that if we do that, it actually performance drops. If we use English predicates rather than randomly generated predicates or synthetic predicate names, the English predicate version performs poorly. And we think it's because the LLM is getting confused. No. So I'd be curious to see how it can inform truth maintenance there. Yeah, so you say there are invariants and they are checking invariants, whether the invariants hold in what the LLM is doing. Yeah, it would be a similar line of, a similar idea, I suppose. Our focus here was to specifically try to see if first we could have an objective measure of assessment, right? Rather than going back to ground truth and the human considered this, right? And then looking at syntactic matches. And the second, to see if we could auto-generate it. So if you have a simulator, I can see how you could apply these kind of methods there as well. Yeah. Any other questions in this aspect? So this is, one of the things that we're doing to look at how to do assessment of LLMs. And the idea with truth maintenance comes in because, like Pulkit said, there is a lot of work where people are looking at interpretability of formal language. And LLMs have emerged as one way of trying to bridge that gap. But the question is, how much can you trust the LLM when it translates something that the user can't understand? And I hope the hope is methods like this will help shed light on how LLMs improve and when you could use them and for what kind of syntax. So going back to some of the stuff that we talked about earlier, remember we were looking at user-driven AI assessment as the overall assessment of going from, well, there were possible executions here which are missing, between the user's intent and the executions of the AI system. And there are all these things that go on in the middle, and we looked at how existing AI alignment and AI safety issues can fit into different parts of this figure. But one thing that has remained largely untouched, with very little attention compared to what it deserves, is this part that everything that we do in AI, let's say it's MDP solving or reinforcement learning based agents, there are sometimes guarantees that you will reach optimality in the limit. And we take those as the guiding factors in selecting algorithms. But in fact, in truth, what's going to happen is most of these AI systems are going to be doing suboptimal computation. Even if the reward function was perfect, if all of the other problems were solved, even then the AI system is going to, in real life, do something suboptimal because it can't do perfect computation. That usually won't have time. So one thing that we, I think, need a lot more work in is how to do assessment that takes into account the system's bounded reasoning capabilities. That is, when it does suboptimal computation, how is it going to fail and how is that going to impact everything else here? So that's one of the gaps in research that I wanted to highlight. But we have some time, so let's open it up for general discussions and so on. So we'll stop here. Thanks.